Hello everyone. In this part of the course, we will be discussing a technique known as depth from defocus. So this, as the name suggests, we will try to extract information from the extent of defocusing that is captured in an image. So this is basically an imaging based technique, and this has a lot of applications, but we will be focusing on a very particular application which is related to a measurement made frequently in the context of fluid mechanics. So before diving deep into the technique that is depth from defocus, we will first try to understand the fundamentals of how a blurred image is formed. With the advent of modern cameras that is easily accessible to I think everyone in the world, like each and every smartphone nowadays consists of a very powerful camera. So I think everyone in the world is now aware with the terminologies like in focus, out of focus, or blurred images. So from a most general intuition, one can say that blurring relates to the loss of sharpness or details in any image. And a scene when captured, if it is blurred, then there is a loss of information. So there can be a lot of reasons for this blurring, some of which we will discuss. Apart from this, if we want to extend this idea of blurring or deblurring, so this relates to image restoration. One of the relatable examples could be security surveillance. Apart from that, there are like wide spectra of applications from medical imaging, photography to even astrophysical, like the images that are captured at astronomical scales. So there, this restoration of information from a blurred image, a blurred signal, is something which is very important. And a natural extension of this idea, being a fluid mechanics person, is to estimate to establish quantitative measurements from blurred experimental images. So, as I have discussed in the last slide, like there can be a lot of reasons for blurring to happen. So, some types of image blurring I am depicting here just to make you realize that you must have seen these kind of images, but I just want to emphasize on the reason behind this kind of blurring. So, the first image here, if I can just put on my pointer, this first image here is because of the camera shake blur. So as the name suggests, this is because you shake your camera just before capturing your image, and this is one thing we all have experienced because of our shaky hands, or maybe we are sitting on a boat trying to capture a beautiful sceneries or something like that. And so you will see that okay, things kind of look hazy and maybe have a directionality in that haze. So that is one kind of blurring that we are all familiar with. This second kind of blurring, which is actually what we are more interested in this course, is this out of focus blurring or defocus blurring. So this is related to the fact that when you have an optical system or a camera trying to capture an image, we all know from basic ray optics or even from intuition that there is a specific region where things look sharp and crisp, like spatially. So in front of the camera, there is a particular kind of a plane over which if you place something, it will look very crisp. But if you move that object away from that plane towards the camera or away from the camera, keeping the camera fixed, you will see that it becomes more and more blurred. So you can also control the extent of blurring, like how it changes as you move away from that plane. But there is always a blur, and this is known as out of focus blur. So this is also a very common kind of blurring, and I think most of like the people might be aware of it. We will discuss why this happens, and how we can then use like the information, what kind of information is available in such blurred images, which we can use to get some quantitative estimates. So that will be the major focus of this part of the course. Then there is this third kind of blurring, which is this moving object blurring or motion blur. This is also a very common form of blurring, where you will, if you can see here, this bus is moving in this right direction, and in the motion, in the direction of motion, you will see the streaks. Okay, so here, most of even artists use this effect to depict motion, but sometimes this is not necessary. Like we want to avoid it, especially in case of like experimental imaging. Say you have an object, if you want to track an object by capturing a sequence of images and then tracking where it went, like with through the sequence of images. But if this streak is formed, because if say if the object is moving at extremely high speed, then a streak will be formed, and then it becomes very difficult to define where the object was, because the streak is like a hazy blur. So that makes things challenging in certain ways, but artistically it looks good. Then there is this mixed blurring, where there can be multiple mode of blurring superimposed. Say you have a defocused scenery, so what the things you try to capture is not in your plane of focus. Then you also shake your camera, and maybe the objects are even moving. So I think this is a perfect picture depicting all of those. And there can be even more categories of blurring that I'm not explaining here, but these are the basic categories I think which everyone can relate to. And some of them we even try to avoid in experiments, like we try to avoid this camera shake blur and the moving object blur, uh, depending, or obviously depending on the context of the problem, but this is something which is very important. And this out of focus blur is something, or the defocus blurring is something which we will focus on mostly. So one of the motivations of implementation of this technique would be dispersion site measurement. So by dispersion, we mean particles dispersed in a fluid phase. And by particles, it's still not a very strict definition, because in a conventional way, by particle we mean solid particles. But here particle means discrete isolated objects. So it can be like a dispersion of liquid in a gas, which is droplets or sprays, or gas in a liquid, which is bubbles, or liquid in a liquid, which are like emulsions, where these both of these liquids are usually immiscible. Or you can have solid in gas like dusts, or like these kind of pollutant particles in air. You can have solid in liquid like colloids, like mud or some slurry, something like that, in a particular concern, obviously in a particular concentration limit, but something like that. You can also have solid on solid, which is kind of unconventional, so it can be a textured pattern. So you can have a speckled or dot pattern over a surface. So it is also kind of a solid entity dispersed over a surface, something like that. And here there is this one demonstrative image uh, of droplets dispersed in a volume. So it is an image of a spray. So you can see, depending on the position of these spray droplets, it can either be in focus. So this spray droplet is in focus because it aligns with the plane of focus of the camera. But this is way beyond that, and that's why it looks blurred. These are even more further apart from the plane, and that's why they look like extremely blurred. So you can see here that each of these droplets or particles are blurred by a different degree of blurring, and that is represented here. So this is a particle image when it is in focus, and when you move that particle away from this plane of focus, you see that it becomes more and more blurred. So clearly here, if you want to extract the size of this particle, it's pretty easy. You can use a lot of image processing algorithms to estimate the size of this particle. I will just say two of them. One is you can directly enclose this within a rectangle or square, whatever, and you can then just estimate the distance from this point to this point, or this point to this point, and that will give you a diameter. Other approach is estimating the area, and then knowing that this is kind of a circle, you can use the formula of the area of the circle to estimate its radius or diameter. Because there is a sharp interface here, things are easy, but there is no sharp interface here. It's a gradual variation. So where should you take that size? Then that's a challenge. And as you increase the blur, it becomes even more challenging. And it becomes even more challenging if you just increase the volumetric concentration of the droplets, or basically if you have a denser spray or dispersion. So clearly here these particles are sparsely spaced, but here you can see like then there are these overlapping images. So that itself is a different category of challenge altogether. But we will focus on this part of the problem, like identifying the size. So that is the final goal, like identifying the actual size of this blurred particle, and estimating where it lies in in the depth direction. So that is the motivation. Here are some of the ideas where this problem of estimating the dispersion size is relevant. So the first problem is actually something what I am working on. So here we see secondary atomization of a droplet because of shock waves, and you can see it generates a lot of tiny droplets. And from this image, definitely it cannot be measured. So we take images at slightly higher magnification, and then as I have shown in the last slide, the dispersion of particles in the volume, and then there you will have some particles in focus and most of them not in focus. Then these kind of depth from defocus kind of arrangement is extremely important to measure sizes. You have also other applications like fuel injection or droplets generated by a rupturing bubble. So when a bubble ruptures, it leaves a trail of droplets, and there also it is very difficult to measure these sizes because it leaves a tail as it moves in and out of the plane of focus. So there is a lot of droplets which is not in focus. Then you can have also bubbly flows. You can have these biological entities dispersed in a fluid media. You can have powder or particle dispersed in air or liquid. Then you can have these target dots on a surface which is 3D, so you have a depth effect. So if you take a normal image with focus over this surface, you will find this surface to be blurred and the other surfaces to be blurred. So this kind of scenario keeps on repeating in a lot of problems where we want to estimate either size or depth or both of these dispersed entities, and hence we want to develop a technique which makes this easier. So now let's dive into the fundamentals of image formation through ray optics, and then extending these ideas for how a blurred image is formed. So that is how we are depicting an image formation through a schematic here. So there are few major components associated with this. So this depicts basically an imaging system. So you have a lens, an aperture uh, coupled with the lens. So you have an opening diameter of d for this aperture, and then you have a sensor plane. So basically this consists an array of sensors which receives the light signals and convert it into a digital signature, which is then finally converted into an image that we can see on our computers or a digital device. And then there is one more thing on image plane. So basically this is the plane over which the image is formed. Then you have this plane called object plane, the plane over which the object is placed, or the plane of focus. So basically we will interchangeably use this. So here we consider a point source for simplicity and understanding. Usually all the objects that we are see are a cluster of point sources. You can imagine it in that way. So this P is a point source, and you can see we can trace rays, and these rays intersect at this point P dash. So this P dash is your image for this object P, and this lies on the imaging plane, which is exactly aligned with your sensor plane. By this we mean that this system is configured in a way that this point P is in focus, and it forms the image exactly on the sensor plane, so that whatever image that is being captured by the camera is in focus. So then there are these other terminologies that I'll just reiterate. So this is something which you already know from the basics of optics, but I'm just reiterating because then that makes things easier. So then there is this distance of this object from the lens U, distance of this image from the lens V, distance of the sensor plane from the lens S, and this focal length of the lens. So these are the basic terminologies. With that clear, now we will talk in terms of things being in focus or not in focus. So first of all, what is the role of aperture? So aperture limits the light, the cone of light that will pass through. So basically this too looks like a line, but if you can imagine this in a three-dimensional way, the lens is circular and the aperture hole is typically circular. So this will form, these are just the two lines of the part of the cone that will pass through the aperture. So if you reduce the aperture, this cone will become shorter, and we will discuss that just in a few slides. Apart from that, these terms are related by this thin lens formula. So this will be very useful in a lot of discussion that we are going to. So the only thing that is important is here a point source generates a point image. So that tells us that the point P is in focus for this system as the imaging plane and the sensor plane aligns. Now we will start tweaking our camera, like the configuration of our camera or the object. It's just a relative configuration, and see how things turns out to be. So the first thing that we will do is just adjust the camera focus. What do I mean by adjust the camera focus? I'm just modifying this parameter S. So whenever you try to say if you have a DSLR and you try to adjust the focus of the camera, you are basically changing the relative orientation of the lens with respect to the sensor plane. So what you are changing is this parameter S. It can be more complicated than this, but in a very simplistic way you can say that you are changing the S. So what happens is now the imaging plane still remains the same as was there in the previous slide. So the image still forms at this distance V, but now you have shifted your sensor plane to this new position with a new S. Okay. So now you can see that this imaging plane and the sensor planes are not aligned. And what your sensor now will capture is not a point. It will capture a circle. By circle, because this is a cone. I explained it in the last slide, right? So as this is a cone, a plane cutting the cone will be a circle here. So this circle is now representative of the blur. How? Because your object is a point source, but now that information is spread out over a circle on the sensor plane. So the image that is being captured in the camera will have blurring. So here this smearing out of information or smoothing out of information is related to blur. So that is what we will define as blurring, the spread of a point source information over a circle. This circle is known by as a blur circle or circle of confusion, or there are a lot of terminology for this, but we will call it as a blur circle in this course. And this kind of configuration now tells us that P is out of focus. So what this means is, as we have changed S, then there is a different U now for which the focus, the P will now be in focus. So basically you have to shift P to in this Z direction. So this axis is the Z direction. So you have to shift P in the Z direction to adjust the focus now. And from simple geometrically similarity, actually you can correlate these terms. So this comes from the fact that this triangle, this bigger triangle, and this smaller triangle. So you have two triangles which are similar. You can apply simple geometry to get this. So I will not be explaining that in detail, but it is a simple exercise that you can try. Now, as I have discussed, now if the C is larger, this size of this blur circle is larger, the blurring will be higher. So basically, more is the spread of that point information over a larger area, so it will be more blurred. So it can be clearly deduced from the intuition. Now let's go back to the first step, and instead of modifying the relative orientation of the lens with respect to the sensor, what if we shift the particle away from the plane of focus? So this OP actually represents the plane over which the particle was in focus in the earlier configuration, but we shifted that particle away from this plane by a distance delta z. So clearly now we have changed U. So the V will also change, or the plane over which the image will form will change. But as we are not shifting our sensor plane, so there is this mismatch between imaging plane and the sensor plane. So the system is again not in focus, and you can see that these rays, after forming an image here, will cross each other and lead to a formation of a circle, as we have seen in the earlier case also. So this lateral shift of the particle in the optical axis direction, which we will mark as Z, leads to a blur circle formation, and again a point source forms a image which is spread over a circle, and we call this again a blur circle, and this means that the image is not in focus. Here again you can use geometrical similarity between this triangle and this triangle to deduce this relation, which looks very similar to the previous relation actually. And from intuition we already know that increasing this delta z, or moving away in the depth direction from this object plane, leads to more blurring, and by more blurring we means higher value of C. So now we will try to deduce a relationship between this delta z and this blur circle diameter C. Here we will invoke thin lens formula mostly to deduce that. So in the initial configuration when things were in focus, we had this formula where the image forms for V equal to S and U equal to U naught, and we can substitute to get this formula. And in the modified configuration where the particle is shifted by delta Z, we have U equal to U naught plus delta Z, as you can see geometrically here. And substituting that in the thin lens equation, we get something like this. Now from geometrical similarity, we can write d by v like this formula. I just have mentioned mod here because you can just see in the last two configuration. In one of the cases we got s minus v, in other we got v minus s. So actually it is much more practical that we put a mod sign here, and then even if you change s without changing the, even for when delta z is 0, you can still implement this formula. So this is a more generic formula. So what now we will do is we will use this relation and these three relations, combine them and like rearrange them to get something like this. So this is something that I want you to do as an exercise, because this is just a simple algebra, nothing else. The only thing that was invoked here is this parameter m, which is nothing but magnification, and you must now know from simple ray optics or geometric optics that m is equal to v by u. So and because of this mod sign that we have kept here, we get this mod sign here still preserved. So this is a very important relation which relates your blur circle diameter c with uh, the aperture diameter d as well as your depth delta z. So this is a very significant equation that will play a very important role when we are trying to deduce delta z from images. So actually that tells us the way in which things will progress. We will try to estimate in some way this C from the images of blurred particles, say just for example blurred particle image, and we will try to use that to deduce delta z, and somehow also use this information to reduce the actual size of the particle or droplets. So that is the motivation, and I will want to re-emphasize that this equation is really important. Now with the same previous configuration, let us see the effect of aperture size on the blur circle. So here you can see that there are two aperture sizes that we have considered for the same configuration, that the particle has an offset with the object plane. In the first case of the aperture diameter d1, which is larger, if we trace these lead lines which represents the ray of light, you can see that it leads to formation of a blur circle of diameter c1. If we reduce the aperture size, what happens is we are reducing the cone of light that is passing through. So although all the other parameters are not changed, so you can clearly see that U naught, U, F, V, all these parameters are not getting changed because of the change of the aperture diameter. But you can clearly see as the cone of light that is passing through the aperture has reduced, you can see the blur circle diameter has also reduced. So clearly for a larger aperture we see that the blur circle diameter is large. For a smaller aperture we see that the blur circle diameter is small. What it tells us is that for the same shift delta z, if you have a smaller aperture, the amount of blurring will be less. So this is a very crucial information, and it has it like if you have ever used a DSLR, you know that you can adjust the aperture to change the depth of field. So depth of field is something which is related to this. So this is something which explains that, which I'll come to later. But here clearly aperture affects the amount of blurring, and smaller aperture means less blurring. And using the earlier equation that we have derived, we can actually correlate this blur circle diameter with the aperture diameter. We see it is directly proportional because V and S and all these other parameters are not changing here. So clearly it tells us that uh, this relation will come out from this. And this is also an important relation which is used in two camera depth from defocus approaches, where you take two simultaneous images with different aperture opening sizes and things like that. So then you need to know this relation, which is very important. So this is the image that is depicting the depth of field that I was talking about in the earlier slide. What do we mean by depth of field? Basically, it means that how much amount of image is not blurred in the depth direction. Okay, so when the aperture opening is very small, as we have seen earlier that only the cone of light that pass through the imaging system is very small, so the blur circle diameters are also very small. So even for very large delta z, the blur circle diameter c will be still small, so the amount of blurring is very small. So here you can see that in this tape you can see only on the farther end, like very far away, you will see some blurring, but for the most of the depth region you will see that everything is almost in focus. As you keep opening the aperture, the amount of blurring increases with depth. So basically even a slight increase in depth will lead to large blurring. So clearly here you can see only things are in focus here, but everything apart from that is blurred. So there is very thin uh, space here in the depth direction where things are in focus. So beyond that, the delta z leads to a very large C and a large amount of blurring. But here you will see that region is much larger compared to this, and here almost for the whole tape you can see everything is in focus. So clearly smaller aperture means larger depth of field, which is a consequence of the fact that smaller aperture means less blurring with depth. And everything that is being discussed here is with depth. So this boils down to defocus blurring now again. So everything that we have discussed till now was related to defocus blurring, which means that when your system goes out of focus, what is the characteristic of the blurring that we see? Okay. So here it is just a schematic representation of a fixed camera system where we see that if the particle was placed on the object plane, it forms an image which looks focused. So here this is a solid a target dot actually. So these both are experimental images. And if we remove that target dot away from this plane by an amount delta z, we see that actual imaging the plane of focused image is here, but we have our sensor plane here. So the blur circle diameter here is c and the radius is r. It's just the same thing. And where we see then the image becomes blurred. So clearly you can significantly observe the sharpness in this image and smooth variations in this image. So this is in focus and this is blurred. We have seen that for out of focus objects with higher depth from the object plane, the size of the blur circle is larger, which means that the blurring is larger. So we have seen that C is proportional to delta Z. Even we have seen that the aperture size regulates the blur. So for larger aperture openings, we have larger blur circle diameters, which means more blur. And this blurring can be explained in terms of point spread functions, which is something which will be a point like the topic of discussion in the next lecture. Uh, just to glance through over this idea, which will be mostly discussed in detail in the next lecture. This blur circle that we were talking about will uh, schematically something like look something like this. So this was your point, and this point information is now spread over this circle. So if I assume that there is an associated intensity or energy of light with this point, that is redistributed over this circle now. So clearly from the law of conservation of energy, you can say that this energy here was it should be same as the energy integrated over this. So you can write it in this form maybe. So this EP represents the energy of this point, and EC is now not a constant value. It depends on the position. So at each position you will have a value of energy or intensity, and you can integrate it over this area, and that should match with this. So this is the redistribution of energy basically. So this spatial dependence here, this spatial dependence of energy or distribution of energy, this is something which is explained using a point spread function. So point spread function, as the name suggests, it is a functional form which represents how that point information was spread over an area. So this is something which we will discuss in detail in the next lecture, which will also uh, tell us how to use this point spread function to simulate blurred images, and that will tell us in a way that how we can use those things to deblur an image. So that's all for this lecture, and yeah, let's discuss point spread function in the next one.